Hi, my name is Cesar Hidalgo and I run the collective learning group at MIT. And what we do in my group is we try to understand how is it that teams, cities and nations learn. Yeah. And to do that, we do two things. On the one hand, we study the diffusion and accumulation of knowledge to try to understand how groups of people enter new economic activities. And on the other hand, we develop tools that integrate, distribute, and visualize data to facilitate learning. Today, I'm going to talk only about the tools. And these are tools that are also being developed by DataWheel, which is a startup company that is spun out of the Media Lab more than 5 years ago and has professionalized the creation of data integration, distribution, and visualization platforms. So how do we create these tools? So these tools solve a very common problem that affects large organizations in the public sector and in the private sector. And the problem is the problem of integrating, merging, and analyzing large streams of data. So if we look at the government as an example, you will see that governments have many ministries, they have many departments, and each one of these departments is a source of data. So for instance, you would have health data on a health authority, you would have data about trade within customs, data about income within the tax authority, you might have data about demographics from the census, and all of these different data sets, if you want to use them together, you have to integrate. That's the first challenge. Once you integrate the data, you can go for a second challenge, which is that of distributing that data. Once you distribute the data, you can start analyzing and making sense of the world using that data. And if you succeed in these three challenges, you might be able to now set up artificial intelligence tools to make autonomous decisions. But how are we doing in the solutions that we're providing nowadays? And my answer is that nowadays the solutions are filled with good intentions. Yeah. Okay? So let's look at a few examples. Here we have the Argentina open data site. So you search for income data there, you click, you find a file, you open, and you get a few numbers that are not integrated, not visualized, hard to make sense of what's happening here. Next, we look at the United States. And if you look at the United States, you also search for income data, you have a similar experience. You get a file with a few numbers, not integrated, not easy to analyze, not easy to understand, what's happening. Finally, we look at Switzerland, and we search here for data for the city of Zurich. We find data for the value added by industry for the city of Zurich, but the experience is not better. So this is not a problem of rich countries or poor countries. Switzerland is very rich, Argentina not so rich. They have the same problem. And the reason why they have the problem is because they have the wrong paradigm. The problem is they think of data as files. So because they think of data as files, as little numbers that are stored inside a table, they create tools to distribute files. But for humans, data is not a number that is stored inside a table. A data set is a set of numbers that we can use to build stories. So what we have been doing is doing tools that help transform data sets into stories. And if we do that, we're going to change our architecture. First, we're going to integrate all of our data. Then, we're going to extract the relevant entities that are common in multiple data sets, such as the cities or industries or demographic groups. Then we're going to identify all of the variables that are connected to those entities across multiple data sets. And then we're going to build stories that integrate all of that information. What this is going to allow us to do is to take multiple data sets and express them as thousands or maybe millions of different web pages. And because these web pages have stories, they're going to be able to be found by search engines. And that way we can get that data to the surface of the web so people can find it and use it. But ultimately, what we're doing is not just simply expressing the data narratively and visually. What we're doing is creating future outlets to be able to connect data to artificial intelligence. Yeah. Just like in the Industrial Revolution, you needed to connect electricity to the refrigerator. In the future, you're going to need to have outlets that connect data to AI. So let's look at a few examples. So if you go to Google and you search for the exports of Korea, Canada, or any country, the first thing that you're going to find is a link to the Observatory of Economic Complexity. The Observatory of Economic Complexity is a tool that makes available international trade data for the entire world, and it expresses into stories that allows you to understand the exports and imports of a country, but also to dig deeper by having follow-up questions that help you go into more fine data cut. Yeah. By doing this, the OEC is able to provide more than 20 million visualizations. But also, it provides a very simple mental model for a user to be able to get to any of those 20 million visualizations. The OEC is a project that we released in 2011. And since then, we've created many projects. In 2013, we created Data Viva that integrated trade, employment, and education data for all of Brazil. In 2014, we created Pantheon that looked at cultural production data for all of the world. In 2016, we created Data USA that integrated data on the economy, health, education, and housing for all of the United States. In 2017, we created Data Africa that integrated data for 11 African countries at the subnational level. In 2017, we also created Jobs KSA that used data on the entire pension fund system of Saudi Arabia to create industry and occupation indicators for all of the kingdom. And in 2018, we released Data Chile that integrate data for more than 15 different government departments. So does this hypothesis work? So here you see the traffic of the Observatory of Economic Complexity since we released it in 2011 until earlier this year. And you see that the pattern of traffic is not that of our news that goes up and then goes down. Over time, the number of users increases. Of course, it goes down during vacation and during Christmas, but now we have roughly 500,000 users every month using trade data in the OEC. Yeah. And all of these users come from organic search. Now, we were able to do the same with Data USA. When we released Data USA in April of 2016, there were many news articles in the New York Times, in the Atlantic, very popular news sources. But you cannot live out of referral traffic. You cannot live from news sources and social media. So over time, the traffic has been growing, and now we receive more traffic from organic search than the traffic that we receive from all of the press that we got the moment that we launched. These tools are also influencing the way that governments think about developing open data sites. Here you have the open data site of the US Census as it is today. Here you see Data USA as we launched it on 2016. And here you have the site that the US Census is trying to build next. So the census is imitating Data USA, and we consider that to be positive impact for our work. Yeah. So with this solution, we win the integration challenge. When you read one of these stories, you don't know where the data is coming from, and you don't have to care. You have data from Housing Authority, or from Transportation Authority, Economic Authority, Health Authority, all in the same story. Yeah. But these tools don't solve completely the problem of distributing data or analyzing data. For that, we need to have other tools. So I'm going to show you a feature of Data USA that we released on 2017. This is the Data USA data card that allows you to integrate multiple sources of data. You just select a data set and you add it to cart, and as you add data to cart, Data USA is going to start merging all of these different data sets from different sources. As a result, you're going to get a data set that has been merged for all of these different sources. This has become one of the most popular features of Data USA. And this helps solve the distribution challenge, because it means that we have an API that now integrates data from dozens of different sources and is able to provide you a custom merge and match table. But we still need to solve the analytical challenge. So for that, we've created other tools. One of these tools is Dive. Dive accepts any type of data set and allows users to create visualizations and statistical analysis within the tool. So Dive is a tool that facilitates transforming any data set into a story. So we tried to test if Dive was effective by doing an experiment. We did this experiment with 70 subjects, which were professional data scientists from Deloitte and BCG. And to all of these data scientists, we gave them a data set that contain information of 1,000 professors from a university, contain information of their salaries, contain information of their experience, their publications, citations, and departments. And we told them this was a hypothetical data set that they had to analyze, but before analyzing, they had to answer a certain number of questions. One of the questions was, whether they expect to observe a gender wage gap in the data set. And 90% of the subjects said yes, and that they expected for men to get higher salary than women. But we prepared a data set that had a wage gap that favored women. So they had to, after analyzing the data, come up to the right conclusion. But we randomly assign the data scientists to use Dive or Excel. And we asked them, after they analyzed the data, if the data confirmed or rejected the hypothesis. When they used Excel, only 57% of them got to the right answer. But when they used Dive, 80% of them got to the right answer. So just by changing randomly the tool that the analyst had in its hand, we were able to change the probability that they would get the conclusion that was reflected from the data. So let's look at how the future might look like if we were to able to integrate all of these tools. Imagine you would like to explore a simple question, such as whether commuting alone to work contributes to higher levels of obesity. Just gathering all of that data, given the way that government distributes the data nowadays, it would be very costly. You would have to spend weeks going to different government websites, download different data sets, and then merging the data to be able to do an analysis. But let's see how we could do this with a pipeline that integrates the cart from Data USA and Dive. So we would go to a map on Data USA, and we would get data from the age, commute time, obesity, and income of people. And after we integrate all of this data, we would go to Dive to analyze it. In Dive, we would be able to just take this data set and immediately make a regression model to predict obesity using travel time as one of the variables that are the predictors, and using the other variables as controls. Effectively, that would create a pipeline that integrates the data on the one hand, but empowers users with the tools that they will need to start analyzing it right away. But nowadays, we're moving beyond the creation of tools, but also we're starting to use artificial intelligence to help automate some of these tasks. So one question is, if I get a wide data set, like a Data USA cart, can I predict which columns will people choose to visualize and how they would choose to visualize them? So to answer that question, one of my students took 1 million charts from Plotly, for which we have both the chart and the data. And then he created a machine learning tool that would allow visualize and which columns of data were selected for the visualization. The tool also would predict which variable would go on the y-axis, which variable would go on the x-axis, to make sure that the visualization made sense. And then we compared these predictions with predictions made by people or by crowds of people. And we found that with VSML, with this machine learning algorithm, we could be more accurate than individual people. We also had an accuracy that was comparable with the consensus of a group of people. We've also been creating tools to capture data about cities. In particular, we're very interested on the physical environment of cities and how people judge the physical environment. And the reason why we're interested on this is because for a long time, theories on architecture and urbanism have had the hypothesis that the shape and physicality of the urban environment affects people's behavior. You can trace this idea back to the 19th century, when William Howells, who was an editor at The Atlantic, invited Charles Merford Robinson, who was an urbanist from upstate New York, to visit Europe and write 3 articles about European cities. Robinson visited Paris, London, and Brussels. And his conclusion was that American cities did not measure up. Robinson was one of the founding figures of the City Beautiful movement. This was a movement that thought that the aesthetics of the city had positive or negative influence on the behavior of people, and therefore urbanists had to be very concerned about the aesthetic of the urban environment. This is an artistic representation of how City Beautiful scholars thought that cities should look like. But since then there have been many movements in urbanism that have influenced the way that we build cities. So 7 years ago we started doing experiments to collect data to test these theories. We began with a crowdsourced experiment in which we had people compare images side by side, answering whether the image on the left or the right looked better or worse according to an evaluative question. Yeah, we asked people which place looks safer, which place looks more upper class, and which places look more unique. We find that the people that participated of this survey had a great deal of agreement. The preferences were very transitive. This tells us that the differences between the quality of the urban environment are larger than the differences of opinion between people. We also modified images to be able to test how individual features affect people's judgment. So for example, using Photoshop, we can clean up the street. We can also remove the wires. And then we can compare the scores that these images get on the site. Of course, we don't put these images never next to each other. We only compare them with other images. What we find is that, for instance, when we resurface the road, people find the image on the right here much safer than the image in which the road is all patchy. But removing the wires, in this case, did not make a significant change. In this other example, we clean up the trash. And we also find that once you clean up the trash, people find the place to look safer. So this allowed us to rate thousands of images in many dimensions. And we find that even though these dimensions were correlated, they give us different information. For example, here is a place that looks classy and also safe. But here is a place that looks relatively classy but very unsafe. Here is a place that looks very unique but not very safe. And here is a place that looks unique and not very classy. So people are not just giving us a general measure of niceness, but they're giving information that is specific to each one of these dimensions. And this allowed us to create maps of people's perception of a city, like in this case, New York. But the good news is that we could use this technique to create maps. The bad news is that you couldn't create maps with very high resolution, because getting people to click on images is very costly, and you can only process a few thousand images that way. So we decided then to use this data we collected for computer vision. What we did is we then grabbed images, we segmented them into different elements, we structured features, and we used those features to predict the score that an image was going to get. This allowed us to create scores for many, many, many different images. And this also allowed us to create high-resolution maps. In this case, this map of New York has more than 300,000 points. The map that we had made with crowdsourced data had only 2,000 points. So now we have maps that have many images per block. So we use then this data to try to understand the impact of people's perception in the environment on behavior. Many years ago, I was part of the first team to publish a paper that looked at people's mobility using mobile phone data. This was a paper that was published in Nature in the year 2008. So what we did was try to use measures of mobility extracted from mobile phone data with measures of perception created from computer vision to ask the question, do people avoid places that look unsafe? For instance, here we look at the presence of people as measured from mobile phone, and we find that, of course, there's more people when there's more population density, there's more people when there's more employment density, there's more people when it's closer to the center, but also there's more people when a place looks more safe. Yeah. But then we separated this effect for different demographics. We find the perception of safety increases the presence of women, but decreases the presence of young people. It also increases the presence of elderly people. And then we could use this data to also understand how the physical environment of the city changes. So we use these computer vision methods on images from 2007 and 2014 to see which are the parts of the city that are experiencing physical urban change. And what we were able to see, or we were able to do, is to create a map of where physical urban change was happening. Here you can see before and after pictures for several parts of New York. And all of these changes were detected using computer vision. So here you see examples in which physical change was positive. The place looks better now. But also we found examples, for example, in the case of Detroit, that physical urban change was negative. And we ask ourselves the question, what are the variables that predict future physical urban change? And we found that the places that have high density of college-educated people tend to experience positive physical urban change. We tested many other variables, but these were the two that were the most predictive. Yeah, we also looked at the geography of urban change. We find that places that were closer to the central business district changed more. And we also find that places that were next to a place that had high street score, high population, or high level of education was also more likely to experience positive urban change. This could mean like physical urban change is, quote unquote, contagious. So why are we building all of these tools? And the reason why we're building these tools is because we're moving to a world that is going to be increasingly more automated. This is a video from a factory in Japan that manufactures solid-state drives. This entire factory is a robot. There's no people inside the factory. But there are many other examples of automation. One of them is the autonomous vehicle. But even though the autonomous vehicle is very famous, it's not the most advanced form of automation that we're experiencing nowadays. For instance, you have the autonomous dump truck. You see, the autonomous dump truck doesn't even have a place for a human to sit. And these dump trucks are already a reality that are operating in many mines across the world for periods of over 10 years now. These autonomous trucks are common in mines in Chile and in Australia. So we live in a world in which we're going to have more and more autonomous units. We're going to have autonomous dump trucks, cars, garbage trucks, and in the future, even construction crews. And in this world of autonomous units, we're going to have autonomous executive decisions too. So to prepare for that future, we need to create good data foundations that are going to help us understand the changing demand that people have of goods and services so that we can instruct these autonomous units on where they need to work and what they need to do. Of course, this is a long and difficult ladder to climb, but it's a ladder that usually involves 3 steps. Usually, the way that you automate things is always the same. First, you identify a problem, like for example, building clothes. Then you create a tool that can help a human solve that problem. Then you study how the human uses the tool to create a tool that automates the human. This was the way that we automated the loom, and now we're automating the car. So by creating tools that facilitate the ability of people to analyze data, we're going to be able to study how people transform data into stories, how people use data to make decisions, so that we can eventually also start doing automated or recommended decisions. And as we change, this way of producing value, we're going to probably change our institutions. We're going to realize that when we contribute data to society, we're participating in a form of civic participation, because that data is going to change the way in which autonomous decisions are being made. So my goal is to continue working with people to make sure that we can build the first step of this foundation, which is that of data integration and distribution systems, so then that the next generation that comes after us could build the other AI systems that are going to help power this new type of democracy and economy. 감사합니다. Thank you.